Good day. RSA is an encryption, decryption system, and is essential for our daily life. If it is broken, it would have consequences for you and me, and the national security. Should we worry now? In this session, I will discuss what it takes to break the RSA, how, and when. Here are the contents for today. I will talk about breaking, hacking, issues with binary, quantum mechanics, RSA, quantum computing, Shor's algorithm. And finally to discuss how far away for people to break the RSA. These days, everybody likes to break something. Of course, break is a nice word. You can call it hack if you want. Steve Jobs once put together an electronic device called Blue Box. It was used to make long-distance call for free. It was illegal, but Steve Jobs was proud of himself for making the device. He even used it called the Pope. You can read more from his biography. I know a person who made long-distance call for free during his college years without using any additional device. Similar to Steve Jobs, he studied how telephones work and found a way to dial it for free. The person may be me. To the left is the famous Enigma machine. It was used by Germans to encrypt and decrypt message. During World War II, it was claimed by Germans that nobody can break it. Well, Alan Turing did. Watch the movie Imitation Game to learn more. Today, the code can be broken within a second, using the statistical analysis method. The right shows a Python program I wrote. RSA is a strong encryption. It seems easy to break, but the time needed to break it is tremendous. So it is considered unbreakable. Using future quantum computers, we probably could break it within seconds. Pay attention, I said in the future, not now. To explain why, let's look at some basic elements in computing. Our computers use binary to represent data. All data are stored in strings of 0 and 1. The advantage is, it is easy to implement and with less errors. For example, high or low, black or while. They are hardly to make mistakes. However, this is not how people interact. For example, a person is either your friend or enemy. This is not true. Some people are just neither friends nor enemy. Another example, the movement of people is not just run or stop, it can be walking in different speed. Another example, according to binary scheme, people live either on the North Pole or the South Pole. This is simply not true. We are in America and there are people in Africa, Europe, and Asia. People live across the globe, not only at two opposite places. Now we see there are issues when representing data in binary. Let's look the example on the right. To find the red apple, current computers check each apple to see whether it is red or green. To start at the bottom, it requires to check almost all the tree to find the red apple. I believe you agree with me that the binary search is not fast, or smart. If we compare computers today with future quantum computers, we can draw the conclusion that the current computers are like the picture in the left. The left picture has only two colors, black and white, symbolizing the current binary-based, digital computers. To the right, is a true color photo that uses 16 million colors, to represent the quantum computer. Quantum computers can take all colors, or even more, at one time. Here we can see, though modern computers are very powerful, future computers could be much better. You can think like this way. The current computer is our Earth. But future computers are the Milky Way galaxy or universe. Let's listen to pieces of music. The left is the best bugle music I have ever heard. It represents the glory of modern computers. But it only has 3 or 5 unique notes. To the right is the trumpets solos by 2 of the great trumpetists. As we know, trumpets use all 12 notes. We can see the trumpets have better melody. We use this as a symbol for future computers, since they can represent more data. In summary, we hope future computers can take more input data simultaneously and process more efficiently. Let's listen. During Einstein age, people discovered some specific properties of quantum particles, later called photons. Light is electromagnetic radiation in the form of waves. The picture above shows a beam of white light is separated into different wavelengths. The red has longer wavelength while the purple has the shorter wavelength. Here is an experiment I conducted to prove the wave properties of light. I inserted 2 polarized sheets into centers of 2 floppy disks. A polarized sheet can only let one direction of light, say horizontal, to go through. This is like a pair of sunglasses that can block the direct sunshine to our eyes. To the left, I put 2 polarized sheets, one in horizontal, and one in vertical. Since light from both horizontal and vertical are blocked, no light can come through. So it is dark in the center. To the right, with both sheets in place, I put a third sheet in 45 degrees between the 2. It is natural we think no light can go through, since 2 perpendicular sheets already blocked the light. However, the reality is different. We see light does go through. Why? Because of the wave property, the light is able to make a turn when passing the middle sheet and turn again by passing the second sheet. As a result, we saw the light. We know light doesn't make turns. It is because the wave property that makes this happen. The drawing shows the proof. Of course, we can turn it into math equations using linear algebra. Let's watch. There are 3 important properties in quantum mechanics: superposition, entanglement, and interference. These properties somehow are hardly understandable. Even Einstein thought entanglement is spooky. Quantum states have phases, and then undergo interferences. When 2 waves are in phase, their amplitudes add. When they are out of phase, their amplitudes cancel. Next, let's look at them one by one. Instead of checking each apple, the superposition lets us to store all apples like a real apple tree. To find the red apple, quantum computers see it directly like a human being, without requiring to search one by one. This greatly reduced the time to find what we want. To solve a problem, computers need to run a series of instructions. The number of instructions could reach 1,000,000 or more. Entanglement by meaning is, all data, and somehow linked together. When you operate on one qubit of data, all others move accordingly. As we can see, this is a 1/1,000,000 saving on execution time. Compare this to a lever. A lever can move heavy objects with just a tiny bit of force. When we throw rocks in the still water, we see waves. Waves have phases. When phases are the same, they add up, so water raises up. When phases are opposite, then cancel, so water lowers down. Mathematically, the operation can be exponential, which is hard to compute. Fortunately, if we transform into the frequency domain, then the operations become additions and subtractions, which is quite easy and fast. RSA is a major public key cryptographic system. Let's pick two large prime numbers, P and Q, and multiply. We got a product, n? However, only given n, to find P and Q are extremely hard, or impossible. That's why RSA is very strong to be used in online transactions, emails, and more. The interesting part for RSA is that, there is a periodic function, means it repeats after the period r. If the period r is discovered, then the RSA is broken. There are many modular, or periodical, cycling, properties in nature. Days in a week equals 7, clock cycle is 12, an octave on piano is 12, or 7, English letters repeats after 26, a stadium cycles every 400 meters. Modular arithmetic is very important in cryptography. To learn more, you can study the number theory. RSA encryption functions like this. Alice, in yellow, runs from starting point, she stops somewhere on the track, which is nobody other than Bob knows. For decryption, Bob, in green, continues running from where Alice stopped, and runs to the point where Alice started, no more, no less. If the process is successful, then it is like Alice sent an encrypted message to Bob and Bob decrypted it to the plaintext. If a hacker, in black, wants to decrypt the message, he needs to know where Alice stopped, and how long to run. This seems very hard. Quantum computers run programs in the following steps. 1. Putting input data in superpositions. 2. Operate on single qubit. Entanglement makes others to operate accordingly. 3. Conduct coupled qubit operations, or interferences. 4. Measure the output to get the result. Quantum computing uses quantum bits, or in short, qubits, to represent data. Each quantum bit is like a sphere. Instead of using 2 points, 0 and 1, in binary, it uses many points across the surface of the sphere. The right is a quantum addition. It takes 3 and 7 and outputs 10. I programmed this circuit using Qiskit, a quantum computing library developed by IBM. It is open to everybody. Next I'll reveal how quantum computers can overperform digital computers. Peter Shaw, a professor at MIT, proposed an algorithm that can significantly reduce the time in attacking RSA. Shaw algorithm makes it possible theoretically to attack RSA with success. I was privileged to study with him in a MIT certificate program in quantum computing. I enjoyed his lectures, though sometime with challenge. The most significant part of the algorithm is integer period finding. The algorithm turns the exponential computation to polynomial. This means a problem that requires billion years to solve, can be solved in minutes. Here is a case using IBM quantum computer to run Shor's algorithm to factor 15. The result is 3, 5. Here is another case using Shor's algorithm to factor 899. The result is 29, 31. You may wondering, these are very small numbers. How about the large numbers used in computing RSA? Well, the algorithm works, but we don't have such powerful quantum computer at the moment. It probably would not happen in 10 years from now. In summary, attack RSA is proved feasible but not now. Quantum computers are in the initial stage with very limited qubits. Hard to compare with the memory we have on digital computers. Even my ThinkPad laptop can have 128 GB memory, which is 1 billion times more memory than many existing quantum computers. This is my virtual machine dedicated for quantum computing. I installed Linux on my PC. The virtualization is provided by Oracle VirtualBox. Quantum computing is powerful. It makes it possible to attack strong encryptions like RSA. On the other hand, it is at the initial stage. A successful attack on current RSA needs powerful quantum computers, which may require 10 or more years. People need to be prepared for the post-quantum age. Now post-quantum cryptography, PQC, study is very active. Quantum computing deals with math, computer science, physics, chemistry, and more. So study well in every subject in STEM is vital. Everybody is able to use quantum computers now for free. Check IBM and Google sites for more information. It is fun to learn. For people who know me, you may wondering this is not my voice. For this presentation, I used natural language processing, NLP, an area in machine learning, to speak my words. On the right, are 2 books authored by me. Check on Amazon or the publisher's websites. It is my privilege to speak to you today. Thank you for your attention, and welcome to the SHI conference, which will be held on March 14th to 15 at University of Oxford, United Kingdom. Have a nice day.